feel to it.
Yeah, it's got an almost improvisational tone.
This semester on Stat 201, prepare yourself for YouTube, because we're all zoomed out. Cahoots and special guests, Tiny Brian, Puppet Shark, Evil Moobot,
I am Moobot.
Morty the Rabbit, and more. Super Statistics Bros.
Hey everybody, how are we doing? The hair just keeps getting longer. Anyways, do we have some questions to start, it looks like? Who has questions to start? I can't tell how to have this jacket. Drop some questions. I was going to do a few, like 2 or 3 practice problems, then head back home. Go back home. Let's start with questions right here. Questions. Questions from students. What questions do you have about the exam? Maybe I'll send the link right here. I'll say live on YouTube right now, currently streaming. I'm still lost on question 4 on the practice exam. Let's go check that out. Taking questions live on YouTube. Taking your questions. Okay, and click here. Okay. So a good, I don't know if we've changed it so much. Let me look at practice 4. Let's go to review 3. I put these links from Moobot in here also to help myself out. Okay, let me make sure this goes to the spot. That works. And then let's publish. And there's review 3. And let's go to the practice exam. So here we are on review 3 practice. And we've changed the questions around a little bit. I hope it hasn't changed too much, but you see questions right here. Let's go see if we go to the practice exam right here. And question number 4 on the practice exam. Let's take a look at it. How's everyone doing today? Let's just wait for this to load. Is it going to load? It's going to load, right? Let me see if we got our planning UTK up. 2 hours later. Is it really just going to spend all day here? Is it going to load? Briley, if you could post a screenshot on the Discord, I can go grab that. Okay, we got a bonus point. Might have to take that screenshot from the Discord. I have some too. Yeah, can you go through a relationship between sample size, standard deviation, and confidence? Oh yeah, we can do that. Let me grab this. Oh, it loaded. Let me grab this right here. Lindsay, thank you so much. Good to see you, Lindsay. Office hour. Hey, we got the office hours people here. Briley's here. Lindsay's here. Mainly how if one gets bigger and smaller, how it affects the confidence level. Can I? Yep, graphing calculators are allowed. Graphing calculators are allowed. Okay, so here we go. Let's do this. Okay. And here we go. Question number 4. Good to see Alexander and David. Currently doing question 4, and it's right here. So this one has been altered from the previous. I think is it only this one? Okay. And so this is the following output is some of the stuff here, blah, 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 blah. And so now let's go back over here and let's see, is there a video for it? Now, I'm not saying watch the videos, but it should be about here. Tested mean. And if you see Terry's just updated the output, does this make sense, Briley? Terry just updated the output because we didn't want it to look like jump output anymore. So it's just a different way of viewing it. And so these videos right here, hopefully I explain it, but we're going to go into a little more detail here. Good to see you, Danny. And also Maddie. Let's go through this because I never would just say, go watch the video. That's not what we do here. We actually explain it. Okay, so you're given a lot of stuff right here, right? You're given a lot. Let's see what we can identify. Good to see you, Aiden. Sorry if I mispronounced the name. We have here the sample mean. We have the confidence level. And probably the confidence interval is going to be some of the best stuff. Does everyone see the confidence interval down here? Let's say this is trying to figure out, on average, how many candy bars you eat in a year. Because candy's good. So what would this be? Who can start out this interval interpretation? You've been collecting data on yourself for 15 years on how many candy bars you eat. So, or rather 33 years of collecting data on eating candy bars. So what does this mean? You got like 21, 18, 28. You're looking at how many candy bars you eat a year. What does this interval mean? I don't care about the other context. I'm doing candy bars eating. What does this mean? What would this interval mean? Who knows? What would this interval mean? Does anyone know? I am what? I am what? I am. I'm 95% confident the true mean number of candy bars I eat in a year is contained in the interval. Exactly. That's exactly it. The truth, right? That the true mean, it's always the true mean. Never the sample mean, because the sample mean's up there. We know what the sample mean is. We know what we ate on average. But the true average, like for all time, for us forever, right? So great work there and good practice. So I want us to think, we have over here a hypothesized value, right? The hypothesized value is going to come into play. That is the biggest pen I've ever seen in my life. The hypothesized value is 22. What is this in notation? Who knows what the hypothesized value is in notation? RotoWave, it's actually this semester for previous students. Come back to UT. You have to come back and take it. RotoWave bomb in the chat. Danny, not quite. Good guess, Danny. Let's do it. One last RotoWave bomb. 100,000 points RotoWave bomb. It is mu naught. It is mu naught. And this one is Y bar right there. That's the sample mean. And that's the hypothesized mean. Good to see Abigail and Caroline. So mu naught is the hypothesized mean. So what do you notice about this interval right here? Can you explain how to tell what test it is just by looking at the output? Because this is a really good question. How do we know what test it is? Well, I'm going to circle the hints in orange. What hints do you see that I'm circling in orange? What hints do you see on this output that helps you know what test it is? What do you know? Maybe I haven't seen Maggie's Kahoot. It's the t-test. It's the one sample t-test because we're comparing one mean. There's not two groups here. We're just looking at, my context is how many candy bars do you eat? So but make sure to put in means there is Mr. T. He's mean because we're doing Mr. T. Now, that two-sided does not mean two samples. That means you're doing the does not equals alternative, which is right here. So that is related to this. That two-sided means you're doing the does not equals alternative, the two-sided test. So it wants this p-value, right? So I want you to think about what we know. So that's the context of this. The value, I'm going to circle this in green. Let's go blue. The value of 22 is where? The value of 22 is where? Think about where 22 is when you say I am 95% confident that the true average amount of candy bars I eat in a year is contained in the interval. It's not in the interval. So what does that mean that it's not in the interval? Since it's not in the interval, the hypothesized value of 22, what? Don't look at the rest of the question, but this is the theory of solving it. Like if you know the theory of solving it, since it's outside the interval, what does that mean? Like, do you believe 22? We reject it at an alpha level. You remember how intervals work. If you make a 95% confidence interval, it's the same thing as running a does not equals test with 0.05 alpha. So you can reject this. I'm blocking that. You can reject this at the 0.05 alpha level, which means how many p-values work here? How many p-values? It's a circle the best answer. The answer is very clearly what? So we know we can reject 22. So since we can reject 22, the answer is E. Did anyone see this and they're like, oh my gosh, it's just the value's not in the interval? E. We all know. Markiplier. He's like a strong dude. Markiplier's like, I don't know, maybe playing video games gets you ripped, but I don't know why I'm not that strong. You need to play more video games is the answer. So with this right here, the answer is E. And does that make more sense? 22 is being tested. It's not contained. Exactly. Could you go over power with beta? Yeah, we can do that too. Let's do that. And let me know. I think that hopefully fully explains this one. Please ask questions. That's why I'm here. Like I'll point you in also directions to be like helping out. We got some stuff. So because the p-value is basically 0, it's not basically 0. It's below 0.05. The only and really good question right there. And Charlie's got one too. Let me grab this. Tag me if you want me to go over something. Tag me because I'm trying to grab them, but make sure to tag me. If we submitted our exam, when will we be able to see our exam grade? Probably later this week, maybe Wednesday at the earliest. Maybe. Working Bird wants to know too. The only thing we learned, is this screenshot here? No, it's a Word document. So the only thing we learn by 22 not being in the interval is what? The p-value must what? 22 is not in the interval, and the only thing we learn is what? By 22 not being in the interval, the only thing we learn is what? By 22 not being in a 95% confidence interval, the only thing we learn is what? It's over there in blue. The p-value must be less than 0.05 for the two-tailed test. Exactly. The does not equals two-tailed test. P-value must be less than alpha of 0.05. Exactly. And the only answer that suffices that is this one here. So it's the only one that is statistically significant. Exactly, RotoWave. RotoWave, so good to see you. Were you in the semester with Mr. Pickle Sandwich? I've seen him twice now. Really great guy, and I even included him in our form. I should put RotoWave as the name. Let me do this real quick. RotoWave, you are also going to be immortalized, and we're going to do our next question. But we have a form this semester. Wait, where's alpha on the chart? Because 95% confidence. Good question. It's because 95% confidence relates to the 0.05 alpha. Does that make sense? Since you know this is a 95% confidence interval, that means it relates to the 0.05 alpha. Does that make sense, Briley? Let me know if that doesn't make sense. But since it's a 95% confidence interval, that relates to doing the same thing. It'll come to the same conclusion as the 0.05. And then, well, you don't just assume 0.05. It's because it's a 95% confidence interval. So since a 95% confidence interval was created, if this was a 90%, this is a really good question. If this was a 90% confidence interval and it didn't include the value, what would we know? If this was a 90%, like the question says, we create a 90% confidence interval, what would we know then? What would we know then? We would know that whatever the p-value is, it would have to be less than point. Like if we reject the value, the p-value, whatever it is, would have to be less than 0.10. And RotoWave, you are officially immortalized over here again this semester in our form. So we have right here YouTube name, Mr. Pickle Sandwich or RotoWave right there. And I'll keep that around just so when students enter it in, if they have a different name that they use that they feel like I won't recognize when I enter in points. It was used on a review question. Why were we using the Z, but they gave the T, then the work. Can you tell me which one that is, Maddie? Tell me which one that is, Maddie, and then we'll do that next. Okay, two-tailed test means the alternative is does not equal, so you can do it on a test. Great job, John, right there. Yes. John, is someone answering? Are you answering Danny's question? Why can we do the two-tailed test with one sample? Exactly. So let's review this. Really good answers / questions. So let's do tails and samples. Okay. So one-tailed tests are either less than, greater than. So the tails of a test, and we're going to do the other questions, how you shade your p-value based on alternative. So you can do this for any of them. Does that make sense? You can do a two-sample, one-tailed test. And then the two-tailed test is the does not equals. It's just the does not equals. So it's the does not equals. Does that make sense? And John did a great job explaining it right there, that the tails goes to whether you're doing like a less than alternative, a greater than alternative, or a does not equals alternative, which would be double. And then the samples are either one sample, which could be, we only do like one sample proportion and one sample mean, which is one sample T, which is Mr. T mean. And this would mean how many groups you're comparing or how many groups there are, how many groups were taken. Like I want to understand how many candy bars I eat, but if I compare that to how many candy bars my brother eats, I'm now doing a what? So if I want to compare how many candy bars I eat to how many candy bars my brother eats a year on average, I'm now doing a what? It was Jake's review? Oh, yeah. Maybe if you drop a screenshot in Discord, I can also get that. If I want to do how many candy bars I eat versus how many candy bars my brother eats a year, like over the last 30 years, I've collected data. Over the last 20 years, he's collected data. We want to compare how many candy bars I eat and how many candy bars he eats. then it's called a 2 sample T. 2 sample right here. And that would be 2 groups, or 1 sample, 2 sample T. And this is for means. What do you think there is? Did you know what? There's also, just get ready to get shocked.
Wow.
There's also, we're not going to do it, but 2 sample proportion, where you compare the proportions. I gotta say, huge shout out to RotoWaves group right there. Shout outs, enjoying some time watching Stat Tool 1. We're rooting for, that's really awesome to hear. Hope you guys had a great project. Mewbots here in the chat. Let's take some more questions right here. Okay, so we've got this to start. K-Brew Bagels. Ooh, good stuff right there. Shouts K-Brew. I have some too. Can you go through the relationship between sample size, and I'm going to grab Danny's question next. Can you go through the relationship between sample size, standard deviation, standard error, margin of error with confidence intervals, mainly if one of them gets bigger, how it affects the other? Okay, so what can you print off? I want everyone to say it for the test. What can you print off for the test? What can you print off for the test? Come swing by and get some RotoWave. What can you print off for the test? The formula sheet. We have like 8 more copies at the front of the office right now. The formula sheet with an umlaut on the O. So a formula sheet. So we're going to go grab the formula sheet because I could write these down, but you should familiarize yourself with what the formula sheet looks like since you'll be using it tonight. Come on, formula sheet. You can do it. You're the little formula sheet that could. I know you can. I don't know if it can. I have no... Maybe it's because everyone's accessing the page, but it's being weird. We don't like that. I mean, weird's usually cool, but... Oh, there it goes. Okay. So here are the confidence intervals. We're going to grab a lot of this right here. And confidence intervals, we only need down to here. And let's go grab this. Oh, that's that one. Let's do it on another page. Now... The thing is, when you write your formulas, the standard error right here, it's over to the side, I believe. This would be p hat plus or minus z star p hat q hat over n square root. Does that make sense? The standard error of this one is also written out for you. This is going to be y bar plus or minus t star s over square root of n. The next one, and these are all written out for you, is y bar 1 minus y bar 2 plus or minus t star with degrees of freedom that are wacky and square root. This is the standard error, s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. Any questions on this notation? Because now we're going to get into, it's the UT Wi-Fi. Oh no, I'm sorry, Working Bird. So let's talk about these equations and see how to use them. I'm going to write one on here, but make sure just to know those formulas exist, where to find them, how to write them out. So here's the first formula I want us to talk about. The first formula is p hat plus or minus z star and then p hat q hat over n square root. First big question right now. Yeah, for the complicated one, correct, Stephen. First big one right now is going to be, and David, I'll try to cover that too. The first big one is going to be, when do you use this? Who can tell me when we use this formula? When do you use this formula? When do you use this formula? Who knows when to use this formula? We're going to cover the topics that the person asked us to cover right there. When do we use this formula? To make a what for the what? When would you use it? Confidence interval for the true proportion, exactly. So the data has to be categorical, right? So we're trying to figure out what the true proportion is. So we don't know what the true proportion is. We just take a sample. Like you go to students and say, have you tried the new Taco Bell? It's a yes, no question. Does that make sense? It'd be called a one sample proportion confidence interval because you're just talking to one group. Like you talk to students and you ask them, have you tried the new Taco Bell? I still need to try it. And so now let's look at the first thing right here. There isn't a standard deviation for this. There's just a standard error. So the standard error of this interval is here. That's the standard error. The margin of error is always what? You should know this. The margin of error in an interval is always where? The margin of error is always where? The margin of error is always where? Some of those, yes, but not a lot of those. Everything can be done by hand without applets and stuff like that. Usually output and stuff like that. Everything after the plus or minus is the margin of error. And I'll kind of give a question that would have you calculate certain things like that. I'll try to, and it looks like the Canvas content. Always the Canvas content is the best way to know what the test looks like. And so then what is this right here? The Z and the star especially means you get to pick how confident you are. Does that make sense? So the Z is how confident you are. Really good questions, babe. And then what do we call P hat? The what of the interval. P hat is at the very what of the interval, which is the sample proportion in this instance. P hat is the sample proportion, which is the what of the interval. P hat is the sample proportion. It's at the very what of the interval. They can be for categorical or quantitative to estimate a truth. It is the center of the interval. The sample proportion is the center of the interval. It's not like a mean, like a quantitative mean. It is the center of the interval, like the average of the interval. That is true, David. But it's not like the idea of like, it's not a quantity. It's not a y bar. So it's not like, or a mu. It's not a mu or a y bar. It is the center of the interval, though. So, and we wouldn't really call it a null because it's not like a test. We'd call it the center, or, so let's write that up here. The center or the estimate. Does that make sense? It's the center or the estimate. So it's the best estimate because it comes from the sample. So now think about this. If we increase sample size, what happens to the margin of error? So we're just going to draw some stuff over here. If you increase sample size, what happens to margin of error? So margin of error will do what? If you increase sample size, margin of error gets smaller. And you can just think about that mathematically because you're dividing by n, so this must go down over here. That goes down. If you make the interval more confident, what happens? If you go from like 68 to 95% confident, what happens as you make the interval more confident? The interval gets wider. Wider, exactly, because you're multiplying by it. But here's a tougher one. If you take, let's put it as a multiple choice. If you take a bigger sample, the interval gets more precise, yes or no? Precise. And don't put it in the tag yet because I'm going to put a poll up. So if you take a bigger sample, the interval gets more precise, true or false? If you take a bigger sample, the interval gets more precise. Does anyone want to answer in the chat now and why? What does precise mean? The interval being more precise means what? Decode what precise means. What does precise mean? So you have to know what precise means. Once you know what precise means, then you're like, well, that makes it easy. When you take a bigger sample, the interval gets more precise. What does precise mean? Yeah, Danny's got it right there. Precise means like a narrower interval. So precision actually is inversely related to confidence. Precision and confidence as two concepts. Like if you make a more confident interval, it gets less precise because it gets wider. So the only way to get more precise is to decrease the margin of error. So the answer is yes. Does that make sense? Basically small. Exactly. Like think about it like as a radius. Like if I'm search over this area or I search over this area, this is more precise than this big area. So a smaller interval is more precise. The two ways to make an interval more precise, good note to have, is to increase sample size or what? The two ways to make an interval more precise is to increase sample size or what? The two ways to make an interval more precise, finish my sentence, is make an interval more precise or decrease confidence. Exactly, because if you go from 95 to 68 or down, the interval gets more precise, but then you lose confidence. So it's inversely related. So good answers right there. Watch this. Here you go. Y bar plus or minus T star. S over square root of N. And now we have a confidence interval for the what? Now we have a confidence interval for the what? Now we have a confidence interval for the what? That's hard to see. Let me do an orange on it. It's hard to tell the differentiation right there. Sorry, my friends who have a hard time seeing. I just have a hard time seeing in general. This is a confidence interval for the true mean created from the sample mean. So what's the best estimate of the true mean? The sample mean. Like you go out and talk to 50 students, ask them how much they spend. The sample mean is your best guess of the true mean. So it's at the center of the interval. Your best estimate of the true mean is the sample mean you see in your data. And it works the same way. If standard deviation gets bigger, we don't usually ask that. That would make the interval wider, standard deviation. Standard deviation is a component of margin of error along with sample size right there. So that's one of our other intervals, the confidence interval for the true mean. And then last but not least, we have a confidence interval for the what? What is this a confidence interval for? Who knows what I'm writing out? I'm writing out a confidence interval for the what? What is this? I missed what you said at the end of class. Did you change with the new books? We changed a little bit. A little bit. There's still, like, you can get a lot. S sub 1 squared. If you can't read, this is on the formula sheet. S sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. And then, wait a minute. Oh, it's not over anything. Oh, what am I doing? What am I doing? Why am I here? Just to suffer. S sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. There we go. So this is a confidence interval to estimate the true difference in means, and we can see the same sort of relationships here. So that's why it's good to know kind of how a confidence interval is created. Can you go over power? Let's go over power. Okay, so what is power? I need a definition of power in the chat. You can give me the definition or the general idea. What is power? I'm going to write out textbook definition. You can Google it. Well, that is, ooh, that's the math of it. Power mathematically is 1 minus beta. That is the mathematical definition. Look at Mubot right there. Are you talking about the ability to correctly reject the false null? Exactly, the probability or the ability to correctly reject the false null. So the ability to correctly reject the false null. Mubot, gotta throw you some Mubot points for Mubot talking there. The probability we correctly reject the false null. And so think about this, it's actually not making a what. So this is not making a what error. So look at the equation. It's the complement of making a what error. 1 minus beta is the complement of type 2 error. Because if you make a type 2 error, you fail to reject the false null. If you don't make a type 2 error, you correctly reject the false null. Like, it's the probability of not making a type 2 error. Because you don't want to make type 2 errors because then you fail to find results. So the kind of like idea of power, the ability to find results in your data if results exist. So if the null is false, you should be able to reject it. So power is the ability to find results when results exist. If you don't have power, what does that mean? You're going to make a lot of whats. If you don't have power, you're going to make a lot of whats. Because think, if your power, let's say your power is something like this. You're going to, but what kind of errors though? Very specifically. That means 90% of the time you fail to reject the false null, or 90% of the time you're making a type 2 error because you don't have the ability to find relationships if relationships exist. But you don't know that you're making type 2 errors because you might actually be making the right choice. So, but a lot of your errors, you're going to make a lot of errors. So how does this occur? There's 3 ways we lack power. Imagine you're watching me play basketball against my brother. So let's go. We're playing basketball, me versus Darren. We're both 6'3", and you watch us play for either 1 minute or 1 hour. Which of these sounds like a more powerful way to run the test? 1 minute or 1 hour? Which of these? So remember, you're trying to have a more powerful test that allows you to figure out differences if differences exist. Which of these sounds like the So how does this relate to our ideas? Sample size. Sample size. A larger sample size increases power. Because if you take more data, you have a better ability to find results if results exist. Does that just make common sense? Like, power is the ability to find results. So if you take more data, you have more power, you have more ability to find results. And then the next concept is going to be alpha. And what is alpha? What is alpha defined as? Who knows what alpha is defined as? Alpha is not the complement of beta. Alpha and beta are inversely related, but what is alpha? What is alpha? Well, it's not 1 minus beta, though. They're inversely related. The probability of making type 1 error, usually set to 0.05. So we usually put it as 0.05, the point at which we reject the null. That's what the alpha level is. And so it's the point at which we reject the null, and it's also the probability of a type 1 error. So you then pick what percent of the time you're going to make type 1 errors. So we have a 0.05 alpha rate. And so what we could do, think about this. What if I just said, let me run my test. Instead of using the typical 0.05, I am going to make the alpha equal to 1.0. What am I probably going to do running this test with a 1.0 alpha? I'm probably going to make a ton of what's-is. Because this would mean if Darren beats me by 1 point, I'm going to be like, wow, Darren's better. Proof. Not that I've proven it. You know what I mean. Probably make a lot of type 1 errors. A lot of type 1 errors. If you think about doctors, could a doctor find every patient who's sick? Could a doctor find every single patient who's sick? And how could they do that? I could. You could make me a doctor today and I could find every single sick patient. They all have lupus. How could a doctor find every single sick patient? Because that would be what powerful test would allow them to, I'll tell you, you walk into my clinic, I say, you're sick. And you say, you didn't even talk to me. I said, too bad, sick. How could the doctor find all the sick patients? And the answer is in this, which is a bad idea. You just say everyone's sick. So you raise your alpha level and you make a lot more type 1 errors. Does that make sense? So making more type 1 decreases type 2 because you'll never fail to find a sick person if you say everyone's sick. Who follows my logic? You'll never fail to find a sick person. That's what the test is looking for. If you just say everyone's sick, which is putting the alpha to the highest bar by saying, let's just reject the null for everybody. This is bad statistics, but it illustrates the point that if you increase alpha and you're more willing to say someone is sick, it makes his own standard for what is sick. Exactly, Aaron. If you're more willing to say someone is sick, you'll catch more people who are sick. So you change the threshold by which we do it. So very important right there, especially very important for immunocompromised people. Think about this. Like, I know some people who are immunocompromised. They've had like transplants. Hope they're doing well. Just thinking about them, especially during this holiday season. And would it be better to make a type 1 or type 2 error? I mean, it's a hard topic, but we shouldn't understand this. So if you think you're sick, it'd be better to what? Because in a type 1 error, the null is true, but you reject. It depends on how you figure it. You get what I'm saying? Like, it really depends, Working Bird, too, because are we thinking like we're sick, but we're looking for evidence we're healthy? Or it depends what the null is. And in that instance, you would want to err on the side of thinking you're sick, but you're healthy, whatever that would be in this case. Does that make sense? So it'd be better to probably make a type 1 error. Yeah, in this instance, the way I'm talking about this is, let me just search this document. The null is, we'll just write null, healthy, and usually we look for alternative, which is the evidence-based one, sick. So a type 1 error in this instance is you reject the null is true, you are healthy, but you reject it and say you're sick. So you don't go and visit your friend who I mean, that means you miss out on seeing your friend, but in a type 2 error, the null is false, but you fail to reject it, so you're sick, but you believe you're healthy. So you could be like incubating right there. You'd rather think you're sick than you're healthy than be sick and think you're healthy, exactly, and like get them sick, especially if they're immunocompromised. So it really depends. Like, I mean, I'll see my parents if I've got like, my parents are fine. If they've got a sore throat or something, they're like, oh, Brian, we'll see you. But if I was hacking up a lung, I'd be like, Mom, Dad, I'm not seeing you. Come on, Brian. My dad's like, whatever, son. Dad, you're in your late 70s. I don't care. Sure, Dad. He's a good dad. A good mom, too. Okay. The last thing that impacts it is effect size. And it's kind of good to talk about like sickness and stuff right here because it kind of makes sense. So type 1 is rejecting the true. No, true, Danny, right there. Effect size is actually how sick you are in this scenario. If we're talking about sickness, it's how sick you are. So this is the true distance between null and truth. That's what the effect size is. So think about this. If you believe you are healthy, but you're super duper sick, are you going to know it? If you believe you are healthy, like the null is you're healthy, you're like, I'm healthy, but you're like, you can't get out of bed, you got a fever, would you reject it? That's a big effect, right? Like you got a fever, you're in bed, you're sweating, you can't keep food down. Guys, it's a fun topic to talk about today, right? But you would reject it. And in that instance, that's a big effect, right? It's easy to detect. But sometimes we get sick and we don't know it. Like got a little bit of cold or something, we don't even know it, a little sore throat, like a little scratch. And so in that instance, since there's such a small effect, we could be sick and then we might make a type 2 error. Does that make sense? So in the instance of a small effect, your test is what to find the sickness? More or less what? When there's a smaller effect, as in you just have a little scratch in your throat, what is the test is more or less what? To figure out if someone's sick. It'd be more, that's the concept we're talking about right now. It'd be more or less what? You have a little scratch. It's less powerful. It's less powerful. It'd be hard to detect. You'd have less ability to reject the false null. Like if you are sick, but it's such a small effect, it'd be very hard to detect. And so let's write this out in another way. One of my favorite ways to write this out is the following. Really? How is it? It's so weird. I think there's an update or something. It's detecting very far. It is not good. It's detecting in a weird way right now. It's detecting and I'm not even touching it. I love how sensitive this is, but it actually looks like it got broken recently or something. Uh-oh. Well, I might be... Oh, now it's working properly. Okay, ignore me. So we have sample size, alpha level, and effect size. And then if those go up, beta goes down. And if beta goes down, power goes up. This is type 2. This is type 1. And this is effect size, this is sample size. So power would go up. And that's 1 minus beta. So when you think about this, if you take a bigger sample, you get bigger power. If you have a bigger effect, you have bigger power. For the basketball example, that would be like, my brother is way better than me at basketball. It'd be way easier. Like, who would be easier to tell the difference between me and my brother or me and LeBron? I play my friend LeBron or I play my brother. Who's going to be able to tell? What would be easier to tell the difference with? It'd be easier to detect that there's a difference between us if I play who? LeBron. And why? Because there's a what? Why would it be easier to tell the difference between me and... You watch us both for an hour. You use the same standard. So you watch me and LeBron for the same amount of time. You use the same standard of criteria. There's a bigger difference, a bigger effect size. Yeah, because the effect size... The null is that we're the same. The effect size is whatever the truth is. You don't know effect size. You can only estimate it based on samples and what you observe. So you'd have an estimate of the true difference, and you'd be like, well, LeBron beat Brian 100-0, and Darren beat Brian 100-2. So, I mean, Brian's just very bad at basketball. Facts right there. Is this making more sense about these three concepts? The sample size, the alpha level, and the effect size, how they're inversely related to type 2 error. And type 2 error is the complement of power. So those are the concepts right there. Good stuff. What do we got? We got a few more questions. Let's take a few more. I was planning to go for like an hour. So we'll do a few more of these. A few more. And then I got to go home and do my work. Work. We did that? Can we go interpretations? Well, we kind of done that a little bit. We did that last one. Statistical significance. Oh, man. Oh, we did this right here. Okay. So your interpretations, I think, are 11 points on the test. 11 points of interpretations. You have 2 things you're going to be interpreting. Who knows the 2 things you're interpreting? What are the 2 things you're interpreting? Does anyone know? You need to know how to interpret this. You need to know how to interpret this. What are the 2 things? Intervals and hypothesis tests. And when it comes to the intervals, it is, and I'm going to have Mubot drop it in the chat right here. That's why I kind of ask it, because then if you put hypothesis first, Mubot's going to do the hypothesis. He's got the pen there for write it down. We have changed it to fill in the blank, and I made sure my test is in compliance with that. So I am blank % confident that the true blank is contained in the interval blank to blank. And then we go here to the hypothesis test. I either reject or do not reject the null. So let's go through hypothesis test first. This is the easy part, the easy way. Why is that easy? That is, I hope everyone gets it. It's the easy way. It's the easy part. Why? What is easy about that? What is easy about that? Just plug in the confidence. Exactly right. I am 95% confident. Now, this is the part people usually get wrong. What always goes here and what never goes there? Well, I put it. What is this for? Is it for the sample? That's hard to see. Is it for the sample or the population? Which of these is it for? It's for the population. It's not for the sample. No. It's not for the sample. Never put sample there. No. Myron, nice job, Myron May. It's not for the sample because the sample we know what the sample is. It's right there. It's 24.03. So we know the sample. We're not going to say I'm confident the sample's in the sample is in the interval. The sample's the center of the interval. The p hat, the y bar, it's all at the center of the interval. And then from this, we'll either talk about for our class, what are the three concepts we try to estimate? The three concepts we try to estimate for the population, which actually, let's fix this up. Tell me while I write it out right here. The three concepts we will try to estimate will either be what? You're not going to write all of them, but the three concepts we try to estimate are what? We try to estimate the true population, what? Don't write all three, obviously. I'm just putting them here as reference. And then you put the context, like the true, mean, difference in means, and then there's one we missed. It's the one we did first. So the means, I'm putting them in order by which we did them. Difference in means. And also the proportion. I got so little sleep on Saturday night. Man, I just had a hard time sleeping. Got up at like 5:30. Not a fun night. And it's contained in the interval lower to upper. So this is just lower and upper. And you would just grab from down here. You would just grab that. 4 a.m. Woo! Man, get some sleep. It's fill in the blank style. It's fill in the blank style. So I am 95% confident the true population mean of candy bars that Brian eats during a year is contained in the interval 22.8 to 25.26. All for the grade right there. Academic weapon. And so now we go down to this one. Okie dokie. New Fallout coming out. It's going to be awesome. I haven't watched the preview. It's just like, once I realized previews just show you way too much, and they're like, oh, we're going to trick them. And some previews trick you, some don't. But usually I can figure it out. Like I figured out a lot of Umbrella Academy Season 1. I figured a lot out, and it was good. I loved it, but don't watch previews. Oh, man, Season 2 Fallout's going to be awesome. Okay. We just started Stranger Things 2, or Stranger Things Season 5. Okay, so with this one right here, you're going to pick one of two paths. This is do not reject the null because it's greater than, and you do not have evidence. What is a synonymous way of saying I do not reject the null? If you do not reject the null, you're also saying what? I like to use it this way. There's a synonymous way you should know. I like to say I do not reject. Like I did not go to the mall. I failed to go to the mall. Does that make sense? Everyone, by my class, you should know I like to say I do not reject this, which means I failed to do it. Because you're like, fail to? It means did not do. I failed. My wife says, did you go to the mall? I say, I failed to go to the mall. She's like, another stat one semester. Oh, no. You're joking, right? We don't accept the null. Yeah, don't accept the null. Don't say, Mubot will freak out if we say accept. I'm trying to remember. I can't remember, and you should know. I think it's important to know. Here's the truth. If you talk to stats people, you have to know fail to reject. They're going to be like, we fail to reject the null hypothesis. If you talk to normal people, which I hope I'm a normal person, it's better to know, like, I didn't reject the null. Like, I did not reject it. It's synonymous, like saying mutually exclusive or disjoint, which you should know both, which are not on this test. This is off topic for most recent chapter, exactly. And tools and techniques. Check out the review sheet. And then if you go down the reject route, you reject the null because your p-value is less than. So we have a famous saying right here, when the p-value is low, blah, 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 when the p-value is high, blah, 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 blah. Finish my sentence. Write it down if you don't know it. What is our famous sentence? When Borgenberg's got the end of it. When the p-value is low, reject the null. When the p-value is high, just let it fly. When the p-value is low, reject the null. When the p-value is high, just let it fly. So the full thing would be when the p-value is lower than alpha, which is 0.05 unless otherwise stated, reject the null. When the p-value is higher than alpha, when the p-value is low, reject the null. When the p-value is high, just let it fly. Does that make sense for people? When the p-value is low, reject the null. When the p-value is high, just let it fly. So there's the sayings right there. I hope a little more context to help people understand what we're talking about. Now, when we reject the null, it's because we have what for the what. Can you go over some question that would be asked about the material? Yeah, we'll do that next year, Rose. You got it. Thank you, Rose. Remind me if I don't do that next, but we'll do that next. When we reject the null, it's because we have what for what. If you reject the null, it's because you have what for what. And this is an important thing to know. Sufficient evidence for the alternative. So did everyone hear that? And good answers? You have sufficient or evidence or enough evidence, sufficient evidence for the alternative. So what is the alternative-based hypothesis? What is the evidence-based hypothesis? The one that requires evidence. What is the evidence-based hypothesis? Which one requires evidence? Like, you need evidence for this hypothesis. The evidence-based hypothesis is what? And people are putting in the chat. The alternative. Evidence for the alternative. Exactly. Like, I reject the null because I have evidence for the alternative. I don't reject the null because I don't have evidence for the alternative. Always the alternative is the evidence-based one. The null is what you believe by default. Like, you're like, I don't think my grade has changed till I have evidence it has changed. Like, you would want evidence, like, you know, like I was waiting for my grades to be entered in. I needed evidence the grade was entered in before I went and checked it. So I got an email like, your grades have been updated. I'm like, oh, that's evidence. I reject the null. I have evidence for my alternative that my grades updated. So in this one right here, the p-value was given to us in later output was 0.00. It was like 0.0. Let's just do 0.008. So I'll write it over to the side. Can anyone? I'm going to see if I've gotten some important texts. My wife is out Christmas shopping. Christmas! I wanted to go Christmas shopping with her. I had to teach. So let's see. Might be... Oh, it's my mom. Minecraft. Yeah. Let me say yes, get that. We're getting Minecraft stuff from my nephews. Oh, no. I hope she got that. Sorry. I'll tell her I was teaching. It was a while ago. My problem is I do kind of well on your reviews and stuff on the exams. Oh, that's all right. Don't worry. Here's the biggest thing. I promise you this. However you do in this class, you'll be fine. And it sounds to me, too, that you're doing a lot of the homework, a lot of the quizzes, a lot of the projects. And I think you'll do good. I think you'll just... The best thing to do is have a positive attitude. You take the test and you say, you know what? I've been doing all the work. I've been doing the homework. I've been doing the quizzes. Worst thing that happens, they make a B. Maybe for some people, worst thing that happens, they make a C. But hey, I think if you're doing the right things, that's what you got to do. Yeah, it's tough. It's tough. I stress about things too. I got a project due on Wednesday, and I'm stressing about that. I got to take my own advice. So you got this, Working Bird. Let's put some hearts in the chat for Working Bird. So Working Bird, we got you there. Do we have to write it out perfectly? No, it's going to be fill in the blank for these. And how many true false are there? I don't know. It's a good question. We'll try to do some true falses. And we do get the bunnies some Christmas gifts. We give them some nice stuff. Let's see. So this one will be, I reject the null that Brian eats on average 22 candy bars because my p-value of 0.008 is less than my value of alpha, which is 0.05, because the problem doesn't say to use any other alpha level. Make sure to check if it says that. This means I do have evidence for my alternative. And this is the does not equals one I was circling right here. I have evidence that the true mean of candy bars Brian eats is not equal to 22. Apparently, I got to lay off the candy bars. So there is evidence for the alternative that the true mean of candy bars Brian eats is not equal to 22. So there we go. And Working Bird, you got this. You got this, Working Bird. We got you here. Okay, we got some other questions here. Okay, so I am going to give you, or I want us to do this in chat. I want you to try to stump me. We're going to come up with a list right here of like so many, put tools and techniques we've learned, okay? Put a graphic in the chat or so our goal right now, and this is going to be a huge review, is you put a graphic in the chat or you put a technique. Like, here's a graphic. You ready? Mosaic plot. Boom. More mosaic plot. Also, we could go right here, scatter plot. Start dropping things. Or we could go here, 2 sample t-test. We'll try to group them. The hacks method. Ooh, that's for any hypothesis test. So any sort of hypothesis test, right? So, Mubot locked in. Can we talk about statistical stimulus? Yeah, we'll do statistical stimulus. Let me do that next right here. Statistical stimulus, you got it. Remind me, Charlie, if I don't do it next. We'll do that next. And chi-squared, I don't want to write. I want to write as many as we can, but I don't want to tell you all the answers. So I'll put graphics up top, and then I'll do tests. But we have more things we learned. We could probably get to 15 or 20. I'll mostly fill out this page. Keep dropping things. There's 2 more tests. So, ooh, regression. Why did that's a test. That's technically a test, yeah. 1 sample t-test. The distributions, which leads to like 1 proportion z-test. What else? I'll put one here. Correlation matrix. That one's often overlooked. This is mentioned very briefly. Hacks is for hypothesis testing. Hypothesize, annotate, check conditions, solve, and state your problem. State your conclusion. Bar chart. Let me put this right here. Bar charts. So, come on. I'm gonna have to do this because I want to do something. There we go. Mosaic. Now it's really a mosaic plot. Contingency tables. Let's put that right here. Contingency tables. Never spell that word right. And bar chart. Histogram. What else? What am I missing? Oh, side-by-side box plots. Why did it do this? Sure. Whatever. It's not on purpose. Let's do at least 3 more. Stem and leaf? Yeah, stem and leaf. Because it's the same as a histogram. Just where you see the number. Frequency table. So I'm putting these together because they could be, so this could also have box plot, singular box plot. Like not box plots, because that's bivariate. Or so we can actually save a little bit of room here. Because we could put this right there, because that's bivariate. The conditions, dot plots, we could put a dot plot. That probably, dot plots won't be mentioned, but yeah, don't be mentioned. I don't think it's on there anywhere. Pie charts, bar charts, and pie charts. I like it, working bird. And trying to think if there's anything else major. Multiplication rule. Anyway, multiplication rule. Put those down there. So I think we have a pretty good mix of stuff right here. Because I want you to look at this. You ready? The first part of this is univariate what? Univariate. Oh, yeah, that's a good question. I think it's not really a test, but it's an idea. I like that right there, Rose. Univariate what? Ooh, I think there is, Jonathan. The first one's univariate categorical. The next one's univariate quantitative. This is bivariate categorical. And this is cat/quant. And this scatter plot is QQ. Does everyone get that? That it starts out with the univariate, and then it goes over to the bivariate graphics. Who follows that? This is the uni versus the bi. Uni and bi. We'll erase some of this text here in a second. Good thinking, Lucy, right there, and we'll good to see you. And then down here, you get to the tests and the 2 sample t-test. Let's see if you can get this. Let me do a poll. So 1 second, don't answer yet. The two-sample t-test uses what kind of data? The two-sample t uses what kind of data? Who knows? Ooh, we're doing better on this. Sometimes I stress some questions and people get really good at it. Light work. Light work. What's he say? Yeah, buddy. Lightweight. So we did pretty good right here. One of each, exactly. Because the two-sample t-test uses a categorical X, quantitative Y. Categorical, is it, did I miss something? The two-sample t does this. It compares the mean of two groups. So the two-sample t does that. We have to know the addition. Not really so much. You have to know when to use it. That's what we're doing right here. If you're doing QQ, what kind of technique are you doing? If you're doing QQ, what kind of technique are you doing? If you're doing QQ, if you're doing quantitative, what are you doing? Please excuse my darn self. If you're doing quantitative, what kind of technique are you doing? Regression, regression or correlation. So regression. So these are interchangeable. If I put it beside it, it's like the same idea. You could just flip-flop either or. QQ. Chi-squared is what, which is a condition known as what? Chi-squared is what, which is a condition known as what? I did one sample t. I did one proportion. Chi-squared has what kind of data with it? CC. And that's called the count data condition. And then proportions is just a categorical variable. Correlation matrix is like Q, 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 Q. Oh, and one sample t is one quantitative. Correlation matrix is where you make a matrix of all the correlations. So it's like a bunch of correlated variables. So you just have a bunch of correlations. And multiplication rule is probability of A times probability, which you have to assume independence, probability of B. And this is probability of A plus probability of B. Okay. So I'm going to give you a question, but then I want you to try to stump me. You tell me the number of the technique you would use in the chat. So the question, I'll write it out for you so you can see it if you're following along. We want to know the relationship between someone living on or off campus and how much money they spend at West Town Mall. What graphic should we use? All right, we want to know the relationship of someone living on or off campus. And what graphic, though? What graphic? So, yeah. Well, so what? Two sample t is not a graphic, though. It would be a two sample t test. That's not wrong, technically. The test to see if there is a difference would be the two sample t, and the graphic would be the side-by-side box plots. Correct. The side-by-side box. Yeah, that's the graphical display. Then the test is the two sample t. Let's try another one right here. We want to know if Brian mu bucks are working. Do students with more mu bucks score higher on exam 3? Run the test. Okay. And if you want to draw, and stacked histograms too, technically correct. That last one could also be stacked histograms. So technically, I don't think we put on the test, but 7. Okay, wait. So identify the variables. There are ways to think about this, okay? But if we say run the test, what are we? So a lot of people are putting. So the tests are more towards the bottom. Like those are the tests. Like the chi-squared is a test. Well, let me ask you. Here's the way to do this. You ready? Here's the trick. How many variables are there? How many variables are there? We want to know if mu bucks are working. Do students with more mu bucks score higher on the test? So you're seeing it, right? Are people seeing the way to do these? And I think we're seeing right answers now. There's 2 variables, and both variables are quantitative. So the right test is regression, and the right graphic is what? And if you draw a little sketch of it, you can also kind of figure it out. If you're like, how would this look? You'd go right here and you draw like mu bucks, and you'd go like test score, and then you do, because we all ace the test with higher mu bucks. So it's quantitative. So it is regression for the test, and the graphic would be scatter plot. Drop one. See if you can trick me. See if you can trick me. Here's one for you, and we'll drop another regression and correlation. Great job, Keegan, right there. Brian goes to play Monopoly at McDonald's. He wants to win on all 8 of his, whatever they're called, pieces. How can you help Brian know this is near impossible? So what technique would you use? We're at McDonald's, and I'm like, dude, I'm going to win on all 8 of these. I'm going to win. Every one of these is going to be a peel-off winner. Because I see you get 2 winners in a row. Like, you pull each of yours, and you're like, I won 2 items. I'm like, dude, I'm going to win all 8 of these. Well, so what number? What number here? What number here? Number what is the answer to what technique to use to help me understand? Did I stump everyone? It is 12. It's 12. The multiplication rule, like the probability of winning on the first and winning on the second and winning on the third and winning on the fourth. Now, since you won, does you winning in any way impact me winning? Does you pull both your tickets and you won, and I've got a whole smorgasbord of items over here, and I'm like, I'm going to win on all 8. Exactly. You winning in no way impacts me winning. And then if I pull 2 of these, they're in no way going to impact the other winners. They're all independent trials, as long as we assume that the McDonald's things are not rigged and they don't put them in a certain order. If they are, like, shuffle them up. So they're all independent trials, and hence the rule for multiplication is independent trials to multiply the probability of things occurring. Is this still about Monopoly at McDonald's? True, it is. Drop one in the chat, see if I can solve it. See if I can do it. Like, come up with your own random question for a certain number. I want to know if students who eat Taco Bell rate themselves higher on a scale of awesomeness. So you're going to compare students who eat at Taco Bell and students who don't eat at Taco Bell? If so, I know which test to use. For randomized questions in the chat right there, what is the test to use? Drop the number of which test to use. We have students who eat at Taco Bell and students who don't eat at Taco Bell. And we want to know how loco or how importante. I'm trying to think. I don't know awesomeness in Espanol. It is. Oh, we tricked people. Or let's get a few more votes in. What do people think? So the thing you want to do with all these tests is you want to identify how many variables are being used. Yep. So you have, do you eat at Taco Bell? Yes, no, that's a variable. And then how awesome do you rate yourself on a quantitative metric? They were very specific about that. So it is number 6. Number 6, Burger King foot lettuce. The key thing is identifying the variables, which is chapter 1. So you have to kind of know some of the knowledge because you have to be like, so Dan, it's good practice right here. What if it is awesome from like not awesome to somewhat awesome to you're awesome, dude, like to totally awesome. So and it would be side-by-side box plots for the graphic. But what if it's like eat at Taco Bell and then it's like 4 degrees of awesomeness in an order of like not awesome, somewhat awesome, awesome, and very awesome. So it's do you eat at Taco Bell, and then what group do you put yourself in for awesomeness? Working Bird seeing what I did to it, right? So now it'd be the chi-squared, and then that would also go with mosaic plots. So there's some of these that are linked. Like as soon as you say the technique is chi-squared, then the graphic for the chi-squared is the mosaic plot right there. Bivariate categorical. If you say you're doing regression, then the graphic for regression has to be a scatter plot. What is a correlation matrix? Ooh. So here's a correlation matrix question. I should have done it and not. I should have just done it and not said it. I should have given you one. I collect a data set on students on their height, weight, GPA, hours studied, and I want to look at the relationship of all the variables. So I collect a data set on students on their height, weight, GPA, working hours. Notice I have a bunch of quantitative variables, and you then make what's called a correlation matrix to view all the correlations. So this is what a correlation matrix looks like right there. It's a way of doing data and analytics, of doing all the correlations between different variables. You correlate each variable right here. It shows the correlation between each variable. Yep, and then you've got a diagonal 1 right here for the same, and then it's a symmetric matrix because it folds over on itself, but it gives you all the correlations between like each variable. Great job, a lot of people doing it. And then Yeah, and then we do shading to show like which ones have high, like these have above 1 and these are below 1. So you can see like negative correlations, positive correlations. And then they usually only shade one side. Is there a categorical variable in the correlation matrix? What's really, I'll show you one thing right here, and then we'll switch topics because we've done a good bit on this. There's a really good package on this called ggpairs. And I'm just going to show you this really briefly because I want to show you some cool analytics. Like what we do, we do cool stuff here. Let me do ggpairs. So, right. Okay. Remind me later. Okay, let me show you ggpairs really quick. I'm going to cheat. But ggpairs uses ggplots. Do you think wait, do you think being a bit shaky in Szechuan? No. I've had students who it's funny, one of my best students like had trouble in 201. One of the students said they got to like 320 everything, then their eyes just opened up. It's always think, am I liking this? Do I enjoy it? And then if you want to do it, that's the real key to it. Never do anything you don't want to do. Don't ever go down the route of a major. You're like, oh, I don't like this, but it'll pay money. And then I think 43, I think we said. Here's ggpairs. There we go. Oh, man. Look at this. So this does a pairwise. It's also got in here the differences for each one. So this is... what is your Clash Royale deck? I don't play Clash. I've been playing Blueprints lately. But if you notice, these are stacked histograms or shadow histograms of each one. And then we have the total correlation right here. And then the p-values for each one. And you can see significant correlation. What's the overall correlation? Wait a minute. What are we seeing? Oh, this is the correlation with the statistical significance. And you can see each one of these relationships broken down with the categorical variable of the different types of flowers within this data set. There's 3 different types of flowers right here. And then the correlation between these variables of sepal length and sepal width and petal length and petal width. And then the different correlations that exist within for the strongest correlation overall right here. And it's very interesting. Oh, it's making it right there. But Vera, whatever that one is, I guess it's the orange one maybe. But this is kind of what we do. We visualize, and we probably label it more and do other cool things. But you can just run it on the data set, like ggpairs, mtcars, and it should run, and it'll make a full matrix of all the correlations between everything. So here we go. This is a correlation matrix. It has like a shadow histogram, but there's ways to add to it. So I didn't use ChatGPT, and that has all the correlation values between everything. But you can just run that instantaneously and get every single correlation between all pairwise combinations of quantitative variables in a data set. And yeah, it gets to be messy. And then what's better is we have something we use. Watch this. So this is how we do better analytics right here. Is we use a library called regclass, which we use in 320. And what do you think this function is about to do right here? This function is literally, just look at the name of it. What did that function just do for me? What did this function, look at the name of the function and then just think, what did it do? What is this function doing for me? It literally gets you what? It gets you all the correlations. And then I sorted it by p-value. Well, it doesn't create a correlation matrix. It just finds all the correlations. It's like 42, 43. I think it says if you click on it. But does that make sense what the function all correlations does? It gets you all the correlations, and then I added additional arguments to it. So the first thing I did is I just got all the correlations, which are all listed over here in a mess to see. Like, that's a mess. And then I went right here and I said, okay, sort them by the magnitude, which is the p-value. And then I said it has to have miles per gallon in it because I said I'm interested in miles per gallon. And then what you can do right here is you can take all this, you can store it into X just for safekeeping, and you could run head of X and get the top 5 correlations, or just throw it on here and go 3 and get the top 3 correlations. So that's the top 3 correlations in this whole data frame with miles per gallon. What's most correlated with miles per gallon is weight, cylinders, and displacement, which have very extreme negative correlations, and you can see them right over here. So what then you could do is you could take your, this is the last thing I'll show right here, you could take your data frame, and you could only take the variables of miles per gallon, and then weight, CYL for cylinders, and displacement. And then you go here and you go to GG pairs in front of it. And now we don't get this clutter of a matrix. We only get the matrix we want to look at. And you can see there's some non-linearity to this. Well, that, yep, miles per gallon with displacement has a non-linear relationship. So last thing I'll say is now we take this right here and we fit the linear model to predict miles per gallon from displacement from the data MT cars. This is data analytics. And then we go right here, we visualize the model, and there's the model, and then we check for the non-linearity. We choose order, and there's the non-linearity. We fit the polynomial model to it, so we go to order, max order equals 2. There's the polynomial model, and then we check the regression to see if we have any sort of issues with it right there. And yeah, or linearity. Where's linearity? Ooh, just barely. So anyways, this is kind of what we do in data analytics. Does everyone get like, I use ChatGPT to get that first graphic, but understanding what you're doing and what you're looking for, the reason you would make a correlation matrix is to simply look at all these correlated values between like miles per gallon and these other ones. You can detect things like non-linearity right here. You see how it bottoms out, it kind of bends because QQ is straight enough, no outliers, plot doesn't thicken. But this is how we do some data analytics, and we search through data and we make graphics. And then what's better yet is you can use ChatGPT. Like if I say over here, make this graphic look amazing, I'm just dropping this code into ChatGPT, and then it'll take what I have right here because it'll know I only want to analyze these variables, and it's going to try to make it look a billion times better. But that's how you want to use ChatGPT. You want to be like, I know what I'm looking for, I know what I'm doing, I know what variables I want to analyze, and then I'm going to tell it to make something better. Bonus, the mu blocks are added to the overall grade. And so let's see right here. It's going to make this better. Oh, and then we have one more question, I think, about p-values and stuff. Okay, and it's doing some colors. You know, we're gonna look at this graphic, then we're gonna do our last question of the day. And I'm gonna go home, do some work. So if you notice, I had one line of code for this. It was simply this, and now ChatGPT is giving me this code, and that's like 70 lines of code for free. But these are the colors right here, but we got to go FF8200. That's UT orange. And here is its graphic for me. It's pretty good. And it broke it up by cylinders. So now you can see, you know, actually each of these is kind of linear within its own. This is called piecewise regression. If we kind of do a piecewise, it works. So this is now, yeah. And that's why using ChatGPT can be very helpful. Like to break it apart. Ooh, there's a positive relationship there. That might just be random chance. Maybe there's just a lack of data. We don't have a lot of, is that 4 to 6 cylinders? No, that's 6-cylinder cars. We never use degrees of freedom to calculate. We'll talk about degrees of freedom. Then I think we have one more on, was it p-values? So degrees of freedom is mentioned how many times for the test? Let's go back to our note sheet right here. Degrees of freedom is mentioned how many times? How many times do we have degrees of freedom talked about? Getting back on topic. I love data. Degrees of freedom. How many times do we mention degrees of freedom? And if you go to the formula sheet, you can see, well, many is true. If you go to the formula sheet, you can see every time we mention degrees of freedom. Statistical, let me drop that here, Charlie, so we don't forget it. We're going to put it right here. Last question. We mentioned degrees of freedom 3 times. 3 times degrees of freedom is mentioned. So do we still have the formula sheet open? We do. The first time we mentioned degrees of freedom is for the what? The first time we mentioned degrees of freedom is for the what? The first time we mentioned degrees of freedom is for the what? The 1 sample t is n minus 1. So you just literally do n minus 1. It's the 1 sample t. You can test one mean. It also is for the confidence interval too. So we should note that it's for the confidence interval and it's for the hypothesis testing. It's just the 1 sample t. 1 sample t test or 1 sample t interval. And you use n minus 1 degrees of freedom. And what's our mnemonic for the 2 sample t? The 2 sample t is what? The 2 sample t is what? What's the formula for the 2 sample t? What is the formula for the 2 sample t? Why is it doing that? I want the whole thing. What's the formula for the 2 sample t? The 2 sample t is what? So if you're trying to remember the formula, some complicated mess, yeah. The 2 sample t is too complicated. The degrees of freedom, it's not like impossible, but it's too complicated. That's our mnemonic for it. The 2 sample t degrees of freedom formula to calculate degrees of freedom is going to be this. That's the degrees of freedom formula. It's too complicated. Look, it's this S1 over, so it's the variance of it, or the standard error of it squared. So that's variance. So it's variance divided by the fraction, but that's not a fraction. That's a correction when you do n minus 1 times the variance. Okay. I'm trying to memorize it right now, but do we have to calculate anything after we solve degrees? So it depends. A lot of questions are broken down into parts. The only thing you have to know for the 2 sample t degrees of freedom is we use it for the 2 sample t-test, and it is not something you will ever solve. Output would generally state it. So I'm going to stop trying to memorize it. I'll memorize it later on my own time. How about the last time we talked about degrees of freedom? The last time we talked about degrees of freedom is what? Which these appear as very easy questions on the test. The last time we talked about degrees of freedom is for what? The chi-squared. So if Brian wants to know if there's a relationship between what day of the week it is and which of your 3 favorite restaurants you go to, what would be the degrees of freedom? Brian wants to know of you test, you have 3 favorite restaurants, and he wants to know day of the week, is there a relationship? Day of the week and fave restaurant, of which you have 3, how many degrees of freedom are there? Be careful. Actually, I think Rose got it. Yep. Wait. It would look something like this. Like, it would be 1, 2, 3, 4, 5, 6, and then it's going to be a mosaic plane or something. Yeah, it's going to something like that. And it is 12 because day of the week has 7, and so you just drop it by 1. You always just drop by 1 and do 6 times 2. So it's rows minus 1 times columns minus 1. So you just plug in and you subtract. Does that make sense? It's rows minus 1 times columns minus 1, and that gives you the shape of the chi-squared, which would look at this point something like that probably. And then you solve for the chi-squared, which is the sum of all the cell chi-squareds. You plug this value in here to get the p-value to the right of it. Those are how we use degrees of freedom. Okay, why do I do that? I don't know. Let's do the last question, then Brian will go home, do some work. Statistical significance and more or less likely. What does statistical significance mean? What does statistical significance mean? Well, it's related to alpha. Related to alpha. In what way? It's related to it. It's not. It does mean rare to a certain extent. Keep going. Everything is correct so far, but I want more ideas. And that's what the relation is. P-value less than alpha, which is 0.05 unless otherwise stated. 0.05. So statistical significance also means we do what? When we have something statistically significant, not kind of, the coincidence is not wrong, but not likely by random chance, because a p-value is the probability of our results, or results more extreme, occurring by random chance variation, given what? The p-value is the probability of our results or results more extreme occurring by random chance variation, given what? I like that right here for this one, reject the null. Because that leads into this. Given the null is true, exactly. Given the null is true. And if you think about some examples of this, you think Brian is a 5-minute mile runner, and he runs a 10-minute mile. So you think Brian claims 5-minute mile runner, and he runs a 10-minute mile. P-value would be what? P-value would be what? Brian claims he's a 5-minute mile runner, and he ends up running a 10-minute mile. P-value would be what? P-value would be what? It'd be high. It'd be high, though. Oh, wait, what is wrong with me? Nope. All right, let's throw out last points. I don't know when. I was like, that doesn't sound right. Everyone's saying it so confidently. Because this was what? Given Brian is a 5-minute mile runner, him running a 10-minute mile is what? I was like, wait, something's wrong. Given Brian is a 5-minute mile runner, him running a 10-minute mile is very what? Given Brian is a 5-minute mile runner, it's very unlikely he'd run a 10-minute mile, meaning you would what Brian being a 5-minute mile runner? Because now there's a statistically significant result because you wouldn't expect him to. It would be way less than alpha. You'd be like, I think we have very good evidence you're not a 5-minute mile runner. So you'd reject the null. So this would mean you observe something very unlikely. You don't have to land right on the null. Brian claims to bench 100 pounds and only did 95 pounds at the gym. So Brian claims he can bench 100 pounds and he only benches 95 at the gym. Would you be like, you're a liar, Brian? I maxed at 100 one time. Hit those would be 32.5s on either. I can't do math today. 32.5 on either side. 25s and 5s and 2.5s. It's usually like 75, 80. It's high 70s, low 80s sometimes. Yeah, it's very close. This is a likely result. So p-value would be higher. And then this is a likely result for the claim. The null is the claim. The null is what you believe unless there's evidence otherwise. This is an unlikely result for the claim. Does this make more sense to people right here? Like, if you just think about it in terms of p-values, where the observed results. So when you think about this, the probability of our results, that's this. And the null, given the null is true, given this is true. So this first one is the probability of running a 10-minute mile, given you're a 5-minute mile runner, is very low because it's very unlikely. And then, because this is the result, it's what you see. You see Brian bench 95, and he's like, I can bench 100. We're like, well, that's close enough. And then we would statistically measure these things. We would have a way of calculating the probability of it. So the p-value is the probability to tell you how likely or unlikely the result is. Can we solve 1 chi-squared? Yeah, we'll do 1 chi-squared. How do you pass the nearly normal if it's data is basically skewed? Yeah, we use the large enough condition, Chris, right there. So we use the large enough n a lot of times, which is the central limit theorem. Exam 3, whatever that was. We got this. We got this, Morbidin. Let's do 1 chi-squared here. Okay, let's do it. And then I'm gonna head off. Go home. Yay! Have you done the 2-sample t-test for hypothesis testing? Kinda. We talked about it a little bit. 2-sample t-test. A little bit. We talked about it. We did some output, I think. Or check out the other reviews too. Yes, good answers / questions. Here we are with a chi-squared test of independence. Brian wants to know if eating out. Let's see. Yeah, let's go. Eating at the new cookout. No, we don't have a cookout. What we got? Whataburger. Increases exam pass rate. Students were asked, did you eat at Whataburger? And did you pass the final? Okay. So what graphic do we need to make? Students were asked, did you eat at Whataburger and did you pass the final? So what graphic do we need to make? Contingency table or mosaic plot, exactly. So that's kind of a tools and techniques question right there. Contingency table, mosaic plot, and we see the results below. And we'd have the following. We'll have Whataburger yes and Whataburger no. And we'll put pass, or we'll just pass fail. It's easier to keep these situated. Nice. We're all morbed in. So we'll pass fail right here. Pass fail. And what we observe is that 100 students tried the new Whataburger and 50 did not. and 120 students passed and 30 failed. And of the students who ate at Whataburger, so I'm trying to think here. The Whataburger students, let's go with, I'm just trying to think the numbers. I want to make this kind of interesting. Okay, that is what percent of them failed? That's a fifth of them failed, right? A fifth failed, okay. So we're going to go here with 24 passed who ate at Whataburger, and we're going to go here with 76 fail. Wait, that's wrong. I reversed it. That's what I do when I do this. 76 and 24. And if you want, while I'm doing this, write the null hypothesis for this. What is the null hypothesis? What is the null hypothesis? And I did the numbers wrong. What is the null hypothesis? So we have, did you eat a Whataburger and did you pass the exam? What is the null hypothesis? Null hypothesis. Okay, I think I have the math better now. 18, 12, 38, 82. There we go. Eating at Whataburger is independent of passing the final, and the alternative would be eating at Whataburger is influences if you pass the final. Exactly. The null is that they're independent, and then we have the alternative being that they're not independent. There's a relationship between them. So the null for the chi-squared is always blank is independent of blank. The alternative is blank is not independent of blank. So now we need to figure out the expected cell count. So down burgers, about me too. I mean, then you get to enjoy burgers too, right? And Whataburger's all right. Shout out to Whataburger. So now we need to figure out the expecteds. And I can kind of figure this out for you, but how many people who eat at Whataburger would you expect to pass? How many people who ate at Whataburger would you expect to pass? We're talking about this one right here. How many people at Whataburger would you expect to, who ate at Whataburger would you expect to pass? Bagel Bites are calling. Oh, Bagel Bites, some good stuff. Nice and soft. You don't overcook them a little too much. Ooh. Problem if they're 200 cooked, there's like ice in the middle of them. Don't do that. How many people ate at Whataburger? It is 80, isn't it? I did the math wrong. Carries. Great answer, Carries. You are correct. I double checked when you said that. I was thinking 75 because I did the math wrong. But I missed a number here also. It's not the end of the world. We should have put 150 here. So this is the formula. Row total times column total over grand total equals expected count, which are given to you. Exactly, Buno total. So we go right here. And what's really interesting about this is the way this one works out, because it's a 2 by 2. As soon as you get 75 right here, that's what that equation solves to. This equals to 75. And it also zeroes in on that. Just think of it as a crosshair. And we are literally taking the row total right here times the column total. Well, good color. Column total right there. And the grand total raw. That's going to be a horrible color. We're not a color. The grand total right there. There's the grand total. Once you solve that one, so did you make up the actual? Yes, I made these up. These are all expected. Or these are observed up here. This is what we see called the count also. These are the count or the observed. It's literally 82 people who ate at Whataburger out of the 100 passed. Does that make sense, Danny? That's the made up number right there. I just made it up for the problem. But 82 people who ate at Whataburger passed. 82 out of the 100 who ate at Whataburger passed. We'd expect 75 to pass by just random chance. And then once you get this number, you can actually solve all of these because it's a 2 by 2, because it has to equal up to the totals. So you would have 100 over here, and this is 25. You have 50 over here, and this is 25. And this has to, wait, that's not right. It's 30 down here. That's why I got it wrong. I was like, that doesn't look right. 30, and there'd be 5 there, right? Am I doing this right? Something seems weird. Something seems weird. Oh, I think it's right. Am I doing this right? Oh, it's because I put 80. My gosh, just don't listen to me. I need to listen to you guys. And I put 75. That's what I had in my head. Remember I told you I did it wrong? That math right there of 120 times 100 divided by 150. And then we get 80, 20, 10, and last but not least, 40. And you can solve any one of these. Exactly. You can solve all these out right here just by moving this around. You would just reposition the numbers in what they solve for. So make sure to know this formula, row total times column total over grand total, and make sure to do the math correctly. Doesn't hurt to do the math correctly. That's very good right there. So now what do we do with these values? Let me ask you this. Yes or no, do you think we're going to reject the null? Because we did see people who ate at Whataburger were more likely to pass. Yes or no, do you think we're going to pass the, do you think we're going to reject the null? Yes, we're probably going to reject the null, or no, we're probably not going to reject the null. Danny says reject right there. If I had to guess, remember I made this up, I'm going to guess the p-value of this problem to be equal to 0.43. There we go. So I'm guessing the p-value is 0.43. So what do we have to solve for next? To solve this problem next, we're solving for what? To solve this problem next, we're solving out what? What do we solve for next? Cell chi-squareds, exactly. So this first one right here, we're just going to show the first one is, so I'm going to highlight, there's the expected. I'm just highlighting only the things for the first one right here. Observed minus expected squared or expected. So this equation is 82 minus 80 over 120 and quantity squared. I don't know how I forgot that. Observed minus expected squared, check your formula sheet. That is 4 over 120, which is, that's a 12th, but move the decimal, which is a third, but move the decimal, which is going to be 0.033, I believe. And then, so that's 0.033. And the next one is going to be the same difference of 2, but dividing by 20. So this one right here is divided by 20. So these are different. Difference of 2, 4 divided by 2, 20. So this next one right here, we'll just put a little thing, is 4 divided by 20, which is 0.2. And this next one is 4 divided by 10. 4 divided by 40. So this one right here is 4 divided by 40, because it's a difference of 2 again. And that's going to be 0.10. And this one is going to be, we'll do it down here, is 4 divided by 10. So that's 0.4. Does that make sense? Yeah, this is very small chi-squareds. I take it back. I think the p-value is going to be even higher. I think it's going to be closer to about that. That's my guess of the p-value now. How many degrees of freedom does this have? This is, did you eat at Whataburger? Yes, no. Did you pass? Fail the final. How many degrees of freedom does this chi-squared have? Has 1 because it's a 2 by 2, which means the curve ends up looking like this right here. We're going to graph it. You wouldn't have to do this on the test. And I think around 2 is there on the chi-squared. We landed at, you have to sum these up. So write this in orange right here. Right in purple. So you take the sum of the cell chi-squareds. The sum of the cell chi-squareds is equal to 0.733. Does everyone see how I got that? Are people following that I found the sum of the cell chi-squareds by... Oh, nice job, Danny. You're right. And then we have to go to the chi-squared applet. So the differences are very small, which means, think only 2 more people passed than we expected. If I say 2 more people passed out of 100 who went to Whataburger than we expected, that doesn't sound like a big difference, right? So you take this right here and you want to find the p-value, and you see that's where, maybe I was closer to my first guess. Oh, man, I should have kept my first guess. I said like 0.4. I should have just said 0.4. Man, I should have said my first guess. Darn it. Should have gone first guess. Should have just rounded to 1 decimal first guess. And we're like, look, 0.4. Like, no way. It's, as the chi-square gets more degrees of freedom, it starts to get a bump. Bump really shows around 3. And then as you go to higher degrees of freedom, it starts to look more normal. And the center of the chi-squared is the degrees of freedom. So if I type 100, the center of the chi-squared is the degrees of freedom right there. So that's how the chi-squared works, kind of visually speaking. You're not meant to know that. It's a distribution that looks like that. At very low degrees of freedom, it's a right-skewed distribution. Any questions or thoughts? Anything? Correct. No need for applet. Nope. No need for applet. We'll show output and stuff like that. I feel really good. I have a macro exam, macro econ. Oh my gosh. Study for that. You got it, Danny. Okay, so when we were writing null hypothesis is the x independent of y or vice versa. Vice versa works. X independent of y, y independent of x. I think it can depend how many true falses. Probably 5 to 10. 5, 10 is a good guess, I'd say. Thank you, Margaret. You're welcome, Charlie. Thank you, Charlie. Good questions. Feel like a girl boss. Love it. Eating chocolate while studying, you guys. Perfect. Perfect. There was some white chocolate pretzels in the office, and I had a few. And we've got some of those truffles with the pistachio or whatever it is. Shouldn't eat them. Shouldn't eat them. And my wife made, oh my gosh. Okay, well, I'm going to send you a picture right here. I'm going to send you a picture of homemade bagels. You ready? Who wants to see? We'll end off right here with a fun thing of my wife's homemade bagels. My wife is she's the girl boss. I gotta promote her like that. Hershey's kind of gal. Oh my gosh. You're about to see my wife made these homemade bagels. She is astounding. I'm going to email it to myself. Okay. Bryce Stevens. Bagels. I am so lucky. Homemade bagels. You have wife boss. I like that right there. You have not, like, bread is good and stuff. My AirPods died halfway through, so I've been listening on my phone, surrounded by people. What's up, people? What is this guy doing? What's he doing? He's going to go home and eat some bagels. I am going to go home, and I'm going to make a bagel sandwich. I should have done more high def than this. Hey, wait. We're not seeing these bagels low def online. We're seeing bagels high def. One last try. Going back to my email. Going to send myself an actual better bagel picture. Okay, here we go. Send bagel picture to Brian and B. Stevens. We're not going to see some low def bagels. Bagels high def. And now we're going to go actual size here. I don't know why I didn't do that. Real ones know my pain with what? Bass boosted. You ever VLC player? I think you can, like, I'm scared for life with the let him cook soundboard. We need that. We need to let him cook. Let him cook. Okay, here we go. Let's check this out. Oh, they look better. This, I'll just show you the last four right here. These are, gosh. You ready to see amazing bagels? Look at these. These are homemade bagels. Homemade everything bagels. They are so bagels. They are so freaking good. They are just golden brown. Everything. I know. She is absolutely insane at these things. Yeah, I know. She's so good at them. She's made them like a dozen times now. They are so, when you get them fresh out of the oven, just you put a little bit of butter on them, and they are so like soft, like and chewy. My wife's like, yeah, let them cool, and I'm like, ah, like she knows. She's like, it's got to cool still. It's got to still like rest or cool and rest, and they're so good. Like I've already eaten this one. That one I ate right away. Yeah, I make sandwiches usually a lot of times with them. So we got a little bit of bacon left from the weekend. You gotta get some bacon, some thick cut maple bacon. And so I'll make like a chicken and bacon sandwich with some hot honey. Like, here's the thing, like learn how to cook and learn how to make your own stuff, because like a hot honey chicken bacon sandwich is gonna cost like so much if you go somewhere else and get it. And like the patties, I use Simply, what is it? Simply something. It's in a green thing. Frozen. Simply Frozen. It's really good. No, that's not it. It's one of them. That's not it. That looks like that. It's really good. Just Bear, that's what it is. That's what it is. Yes. Jonathan knows. Just Bear frozen chicken. That's what it is. That's what it is. Yeah, these things right here. Oh my gosh. You can get them, if you get them on sale. Food Line. Sure. Yeah. You want to get these on sale for like $1.25. Kind of, yeah. Got an air fryer and all that. You put that on a bagel, and you put some lettuce and some like tomato on it. You get tomatoes on sale too. Megan Trainer taught me not to cook. Bagels, or I don't know what that is, Connor. Yeah, this is the exact one I was thinking of. I was like, what is it called again? I just know the bag. I was like, that's the one I want. Publix had them on sale this week. I think buy one get one. So I think it was $1.20 per per chicken thingy. And then we make the bagels for like 40 cents. That's $1.60. The hot honey, you're only using like 20 cents of that. And then you get your veggies on it. So you make like a $2 and the sandwich is like this. Like the sandwich is huge and they put a little chips. I mean, I know that's not healthy, but you got, yeah, basically bagels that you don't boil, kind of flatbread. Oh, interesting, Connor. I'll tell my wife about that. I'll try that. But it's so good. I mean, like, we also make burgers and stuff. Oh my gosh. My wife made pretzel buns. Gosh, I'm just getting hungry. I gotta go home and eat. The pretzel bun. I think I have a picture of the pretzel bun burgers, but they were awesome. Like, I don't know. I share pictures with you guys. We have a family chat. I don't post on Insta or whatever, but she watches a lot of like the homesteading and cooking channels, like Cooking with the Zimmermans or Something with the Zimmermans and Roots and Refuge, like a lot of those, and just learning how to like do better gardening, better everything. 'Cause it's a good skill to have. You should know how to garden, should know how to like cook and bake. I mean, I wish I had those skills. I try to learn the handyman stuff. I built a fence for our gate, or a gate for our porch. Mubot remembers everybody. So it's the more skills you have, I think the easier life can get. It's yeah. But with that, we are about to end. What do people think? Are people ready for the test? What do people think? You're welcome, Connor. Not the Twitch chat. What? Not the Twitch chat. I think so. I feel okay. Not the Twitch chat. Were you ready? Well, Mubot has a short memory. Chat every 15 minutes. Oh, this is it's. Oh, there it is. I'm so morbed too. One last morb to end class. One last morb.
Let him cook.
What?
Let him cook now. Let him cook. I said, let him cook.
Welcome. Great reviews. Until then, bye for now, everyone. Bye. Feel the bass. Bye. We've almost got these new intros ready. We're almost there.
This has been going for like 20 hours. This ends now.